Hello, my name is Jim Bowden. In this video, I'm going to give an explanation of standard deviation and variance. This video is actually an update of a talk I gave 15 years ago. At the time, I also put a video together and posted it on one of my websites. The talk was a toolkit for statisticians, mostly software, but I did provide presentations for several statistical concepts. One was an explanation of standard deviation. About a year ago, I was checking YouTube for videos on standard deviation, and I ran across a couple that surprised me. They were almost word for word the same as what I presented 15 years earlier. But what shocked me was they both totally missed the main point. I went back, dug the video up, and watched it, and I could see in hindsight where I could have made parts of it clear. So I redid the graphics and changed it around a little bit, and let's give it another shot and see how it goes. Okay, let's start with 4 pieces of data. I have 4, 5, 7, and 16. And first thing we want to do is get an average for the data. And you're probably thinking that's pretty simple. I can do it in my head. I take 4 plus 5 equals 9, plus 7 equals 16, plus 16 equals 32. So I have a sum of 32. And I have 4 pieces of data, so I divide by 4 and I get an average of 8. Pretty simple. If I were to ask you to give me a formula to do the average, some people might struggle on that because they maybe have never seen the formula or a formula for it. This is what a formula might look like. I have X bar here, which is my average. Then I have this summation sign, or the capital sigma, Greek letter sigma. It looks like a sideways M. It sum up all my X values, and my X values are up here. I have X1, 2, 3, and X4. And then back to the formula. At the bottom it says divide by N, and N is the number of pieces of data. So let's do the top section of the formula here. Sum up all the X's. That's exactly what we did up here. We summed up our values and we got a sum of 32. Next thing we did was divide by 4. That's dividing by N, and that's what's happening down here. And we got an average of 8, or X bar equals 8. Pretty simple. If you were to think about what this average looks like, you might think of it as on a balance bar or teeter-totter. It's the point that the data would balance at. That's not a bad way of thinking about it. There is a problem, though, that tells us the point that it balances about, but it tells us nothing about how spread out the data is, or the dispersion of the data. We could have 4 values that were exactly the same, all 8, and the average would be 8, but it's a lot different than the top there. Or we could have something that had more dispersion, like here at the bottom, still the same average of 8, but much more dispersion. We need to come up with a way of defining dispersion that we can also use to communicate that value to people. What I'm going to do is give 2 formulas. The first is dispersion, and this lays the groundwork for standard deviation. And this first one, I made the formula up. And then the second will be the actual formula for standard deviation. So let's start out. I thought since average is easily understood, we could define dispersion as the average distance away from the average. The average distance away from the average. My formula would look like this. D for dispersion equals the sum of each of my data values, X minus the average, and then we'll divide, when we get done summing that up, we'll divide by N, and that'll be the average distance away from the average. It would look like this if we look at it on a balance bar here. Take my first piece of data. The first piece of data up here is 4. 4 minus our average of 8 gives me a minus 4. Second piece of data is 5. 5 minus 8 gives me a minus 3. The third piece of data is 7. 7 minus 8 gives me a minus 1. And then my last piece of data over here is 16. 16 minus 8 gives me 8. Pretty simple. Now we'll sum the values up. We've got the values here. We got minus 4 plus minus 3 plus minus 1 plus 8 equals 0. Wow, what are the odds of that happening? Well, actually, that's a problem because it will always end up being 0 because the sum of half of our values, or the values less than the average, will always equal the sum of the values greater than the average. So when we subtract the two, we're going to end up with 0 every time. And that's what we did. What we need to do is get rid of the minus signs here. We need to figure out a way to do that. And there is a simple way of doing it, and that is simply square my result coming out here, coming out of this portion of the formula, x minus x bar. So we got a minus 4 here, we square it, and we get 16. We've gotten rid of the minus sign, and it gave us 4 squared equals 16. Second one, 3 squared equals 9. Minus 1 squared is 1, and 8 squared is 64. So we've gotten rid of all the minus signs. The only problem is, of course, we got these values that are a lot bigger than what we originally had. So we need to get them back to what they were, and we can do that by simply taking the square root. So we take the square root of the values here, and that gets rid of the minus sign, and it gets us back to where we want to be. Okay, now we can sum these up. So I've got 4 plus 3 plus 1 plus 8 equals 16. And then divide by 4 because we've got 4 pieces of data, and that gives me an answer of 4. So D, or dispersion, equals 4. This is what it would look like on a balance bar. It's saying my average dispersion is 4 with the range on the balance bar here. There's a problem with this because I could have something with more dispersion and still have the average of 4. This bottom set here, you can see it has more spread in the data, but still giving us an average of 4. So this formula for dispersion might not be a great formula. But let's compare this to the formula for standard deviation and see where the difference lies. This is the formula for dispersion at the top. This bottom formula is the formula for standard deviation. And as you can see, they look similar. Matter of fact, the only difference is where the square root sign is up here. If I move that square root sign to the outside of the summation portion here, I have the exact same formula. Move it back, that's my dispersion. Move it out, and I've got the same formula as the standard deviation down below. So let's take it back. This top formula, we followed that through, and that made sense when we went through it. Let's take this bottom formula for standard deviation and see if we can make sense out of it. In the formula for dispersion, what we did is we took each value and we calculated its distance away from the average. Here we end up for our value of 4. Its distance away from the average was a minus 4, but we made it an absolute number, saying it's 4 away. The thing is we're working with the one-dimensional 4 here. It's just a distance. Up here, if you look at the formula, we're squaring, over here, we're squaring the value. And so when we take 4 squared, we end up with 16 over here. So we're going to have something that looks like this. We're squaring the values. And what we've done is we've just gone from a one-dimensional line to a two-dimensional area. And that's the big difference between the two formulas. And the formula that we had for dispersion, we're working in one dimension. In standard deviation, these values that we're adding up are actually areas, or two-dimensional. So let's see what it would look like when we start doing it. We have 4 squared equals 16. So I've got 4 times 4. I've got 16 squares here. That gives me a value of 16. 3 squared, that gives me 9. So 3 times 3, I got 9 here. And then I'm summing these up now. So I go 16 plus 9, and that gives me 25 here for this bigger square. So I've added these two squares together, and they come up with 25. Now, if you're like me and you're looking at this, you think, I've seen this someplace before. And if you go back to middle school or junior high school, you may remember Pythagoras and the Pythagorean theorem. That's what we're dealing with. It's the same type of math. And I'm not going to talk about this anymore, but just keep this in the back of your mind as we go through this. So we're back here with our squares. Our 25, again, is made up of the 16 red, and it's made up of the 9 blue. So that's where the 25 comes from. So we bring that down. We're going to move on in our formula to the next one here. We got 1 squared. 1 times 1 equals 1. So that gives us a smaller square here. And we add the 2 together, and we get 26. And you can see I put the green out here. It's a little small border on 2 sides around there. It doesn't have much of an effect. Bring the 26 down. Our next value is 8 squared. 8 squared gives us, 64. And that's a pretty good size. And then we take 26 and 64, add them together, and we get something like this. That gives us a value of 90. Okay, let's roll this around. And what we've done so far is we've summed up all of our squared values, the distance away from the average, and we came up with 90. That's our total area. We can now turn the color to gray. We don't need the colors anymore. And at this point, we have just completed this top section of the formula here inside the square root bracket. Next, we're going to divide by n, our number of pieces of data, which are 4. And that's going to give us sigma squared. So we divide by 4. That's 90 divided by 4. And that gives us an average area of 22.5 is what we have here. And what we've just calculated at this point is the variance. Sigma squared is the variance. And the variance is the average area of our data that had been squared. Now we take the square root, and we're going to finish the formula. We take the square root, and we're taking the square root of sigma squared, or the variance, and it's 22.5, and we get a value of 4.743. We're now back in 1 dimension, and what we have here is the standard deviation. The standard deviation is the length of that square. And there's one more thing I need to cover before I finish. We've been using this formula here, and this is the formula you use when you're using all of the data from the population. But usually you don't have that luxury. You don't have all of the data. You're taking a sample from a population. When you have a sample, this is the formula you want to use here. The only difference between the formulas are if you have the full population, you divide by the number of pieces of data that you have. If you have a sample, you divide by the sample size minus 1. Well, why minus 1? This inflates the variance by an amount based on the sample size. The bigger the sample size, the less it gets inflated. And that's it. We have just defined variance, standard deviation, and the difference between population and sample standard deviation. Hey, thanks for watching. If you have any questions or comments, leave them below. And you might want to subscribe. There's going to be more videos coming out, and I hope you enjoyed it. Again, thank you very much for watching.